Welcome to solverfy.
Consider a lever AB, which at point B is attached to a horizontal shaft BC, which passes through a bearing and is welded to a fixed support at point C, and has a force P applied vertically downward at the other end of the lever at point A. And we want to figure out what the corresponding angle of equilibrium will be, given that the torsional spring constant of the shaft BC is given to us as capital K equals 12.5 Newton meters per radian. The length of the lever L is given to us as 250 millimeters, or in SI units, 0.250 meters. Note, we want to hang on to all three of our significant figures, just get them into the right dimensions for SI units so that everything's compatible when we calculate. And we're also given that the force P has a magnitude of 100 newtons. And we want to figure out what the resulting angle of equilibrium is. And the way we're going to do this is we're going to identify what forces can do any virtual work on our system and express their potential energies so that we can then re-express them in terms of one variable, namely this angle theta, such that we can then use the equilibrium condition, which is the first derivative of the potential energy with respect to theta is equal to 0. And then we're also going to check the stability of those equilibriums, which we'll do by taking the second derivative of the potential energy with respect to theta and comparing that to 0. If it's greater than 0, it'll be a stable equilibrium. If it's less than 0, it'll be unstable. And if it's equal to 0 for this and all further derivatives with respect to theta, it's a neutral equilibrium. And we're going to figure out what we have here. So the only forces in play here that do any work are this force P and the spring force of this shaft BC. So we can go ahead and write an expression for the total potential energy of our system quite easily, in that it's just this elastic potential energy plus the potential energy of this force P. And we're actually given in a hint that the potential energy corresponding to the couple exerted by a torsion spring is 1/2 capital K, the torsional spring constant, theta squared, where theta is the angle it has been torqued from equilibrium, which is pretty much the same as your general horizontal spring equation, but just turned into terms of theta. So we know that is 1/2 capital K theta squared, with theta being the same theta as we've defined in the diagram. And we're going to treat the potential energy of this force P just like we would the potential energy due to gravity, where it's just the force times this vertical distance it's working along. So just P times y sub a. And we're going to define this y sub a again in terms of theta, so we can use the equilibrium condition as just, we're going to define it as from B as our origin, just this height here. So we're going to define it as negative because it's below, but it's just going to be L, the hypotenuse, times sine of theta. So again, this is just going to be equal to 1/2 capital K theta squared minus dl sine theta. And that is the general expression for our potential energy for our system. So let's go ahead and take the first derivative with respect to theta, which is, again, pretty easy here. Derivative of 1/2 k theta squared is k theta, just power rule, 2 times 1/2. And the derivative of PL sine theta is just PL cosine theta. And we can go ahead and take that second derivative now too while we're at it. It's been pretty easy so far. And that's just going to be derivative of k theta is just k, and derivative of PL cosine theta would be negative PL sine theta. So this is going to be plus PL sine theta. And now to actually find the location of equilibrium, we're going to set this one, dv d theta, equal to 0. So again, using our equilibrium condition that the first derivative is equal to 0, that tells us that k theta equals PL cosine theta. Or in other words, we can go ahead and sub in our actual values of 12.5 newtons per meter per radian times theta radians equals 100 newtons times 0.250 meters times cosine theta, which I'm sure you can tell simplifies quite easily into just theta equals 2 cosine theta, which has only one numerical solution, wherein theta equals 59 degrees. Exactly, 59.0, hanging on to all three of the significant figures we had from our initial given values. And now we just want to check the stability. So we're going to check the second derivative of the potential energy with respect to theta when theta equals 59 degrees, 0.0 degrees, sorry. And that just equals, again, going back to this equation, it's k plus PL sine theta. So as we've established, 12.5 plus 25 times sine of 59 degrees is obviously going to be a positive number. If we got to degrees over 180, then this would start getting to, counter against us up until we got past, this having a larger effect than this. But this is going to be definitely positive for at 59 degrees, which means that it is a stable equilibrium. And again, all we did here was we identified what forces could do work on our system, expressed their potential energies in terms of theta, took the first derivative with respect to theta to use the equilibrium condition and figure out where the theta corresponding to equilibrium positions were, and then took the second derivative with respect to theta to use to check if the equilibriums were stable. And we found that the equilibrium point is at 59 degrees, and it is stable.